Good morning, everybody. How are you doing today? I hope it's wonderful. Oh, we got one more. Okay, let's see there. There we go. Okay. So, as Henry Ford says, nothing is particularly hard if you divide it into small jobs. And that reminds me of several of our problem-solving strategies that we've learned this semester and that we will now be applying to our right triangle friends today. So, over the weekend, you read and took notes on section 3.3. Here, then, is the accompanying problem set. I'm going to talk a little bit about this, some problem-solving strategies to make best use of. We'll do a couple examples together, and then I will leave you with the reading quizzes to complete, and any additional time you have in class can be spent on working on the said problem set. Okay? So this section introduced the Pythagorean theorem and right triangles, specifically the special right triangles. So with those two pieces of information, we're going to be able to solve lots of stuff. Pythagorean theorem gives us any two sides of a right triangle, we can find the third side. And if it is a special right triangle, then from any two pieces of information, that is a side or an angle, we can find the other sides and the other angles. We can solve the entire thing, which is very handy when you can say only measure one side of the triangle. But if you can set that angle to be one of your special triangles, you can do a lot with that. So we'll see how that's implemented in some of our examples today, and then apply it to another practical situation in class tomorrow. So for right now, let's look through a couple of these problems. We've got just practice finding that missing side length, using that to find area of other polygons. With a missing dimension here, well, notice that this is a right triangle, so you can treat that as such and work out how to find that one. Why were you marked absent? Probably because I didn't see your name in there earlier. Thank you for alerting me to that. Fixed now. Did I miss anybody else? I don't see him in there. Okay. All fixed. Thank you. All right, where was I? Yes, using that information of finding a triangle to apply it to a situation, right? Some other polygon that can be broken down into triangles. Number 7, I would like to highlight a little bit here. This is a rather tricky one. It tells us the area of a rectangle is 24 inches squared. A diagonal of the rectangle measures exactly square root of 73 inches. I don't know how they measured that so precisely, but they did. Find the length and width of the rectangle. Strategy number 1. Is it number 1? Well, the first one we will use here. Draw a picture. Okay? Here is my rectangle. What do I know about it? I know the area is 24. Inches square, right? We know the diagonal length there, and we're supposed to find length and width. So I'm going to use another strategy. Create a variable. Let's call length and width L and W here. That way, we can now write out some algebraic equations about the information we know. We know the area. We know it's a rectangle. We know the formula to find the area of a rectangle. That's length times width. Well, in this case, length times width equals 24. Write that down. Okay? What else do we know? Well, if it is truly a rectangle, then these are all right angles, which means this diagonal creates a right triangle. We know the relationship between the legs and the hypotenuse. That's Pythagorean theorem. Okay? So we can write L squared plus W squared would equal square root of 73 squared, which is just 73. So there's a second equation. Right? drawing a picture, creating a variable, writing equations. Now, to actually solve for length and width, we're going to draw on our algebra skills and solve this system of equations. Yeah, but it's got squares in there. So this is technically a quadratic equation, even if I substitute from one into the other. Solving a system of equations sounds ugly, okay? I mean, you can do it, but it's going to get gross. This is where I would recommend another problem-solving strategy. Let's assume, for instance, that length and width are integer values. It's not going to be, 4.5. They're just going to be 1, 2, 3, 4, 5, right? Integers. Let's start there. See if we can find a solution there. If that's the case, that greatly simplifies our options here. Right? Length and width then have to be integer factors of 24. That's a fairly short list. Right? It's a lot bigger than all the numbers ever, right? I would go and just guess and test. Say like, hey, what factors of 24, when squared and added together, make 73? Now I would create a table and start testing each of them, right, in combination. That way, I don't actually have to do this solve a quadratic system thing. Oh, wait, I don't want to do that. Let me just try a few numbers, see if they work, right? Yes, it's the easy way out, but it is one of our official problem-solving strategies. It's perfectly valid to use here. I'll leave you to finish the rest of that and find out which one it is. Okay? Any questions on that concept, though? I bring it up because I feel like it's been a while since we've explicitly talked about the problem-solving strategies here. Still very useful. Okay. All right, then the two examples I have prepared for you today are very similar to a couple of problems in the problem set. So they will serve as good practice for you. Number one. How high can a 12-foot ladder reach if it must make at most a 60-degree angle with the ground for safety? Okay? As anybody who's been on a ladder knows, you do not set the ladder perfectly vertical up against the wall, because as soon as you start climbing, the ladder is probably going to tip and fall backwards and you fall down, right? So you set it out a little bit, okay? So it makes, and actually, why am I trying to make hand motions? Let's draw, okay? Draw, here's some ground. Here is a building, and here is my ladder. Okay, I mean we can give it the double sides if you want, right? There, that looks better. There's my ladder. It must make at most a 60-degree angle with the ground. So the angle with the ground would be down here. Okay, we don't want that to go all the way to 90 and have it perpendicular straight up and down. It's unstable there. So the best we can do, let's say it says at most 60. So the question is, do we make it the maximum possible of 60? Or is that trying to throw us off and be like, no, you should actually make it even smaller than that. That'll be better. Let's see here. What if I drew my ladder like this? Okay, if I had a flatter ladder, so a smaller angle here, I definitely end up with a shorter height that it reaches. Agreed? So we definitely want to max out that angle to get the most reach possible. So we're going to stick that with 60 degrees, and the ladder itself is 12 feet. And I want to find how high can it reach. So I want to find this height. Okay. The building, of course, we will assume is perpendicular to the ground, as any height measured should be anyways. So this is now a 60-degree right triangle, which means that other angle has to be 30 degrees, and it's a 30, 60, 90 special right triangle. I know that means that in such a triangle, if this is 12, then this side is half of that hypotenuse, 6, and this side is that half piece times the square root of 3, which means this is my final answer. That's the height. 6 times the square root of 3 feet is how high I can reach. We can get a decimal approximation for that if you want to know. Let me just pull up my calculator here. 6 times 3 square root is 10.39 approximately. Okay. A little more than 10 feet, not quite 10 and a half feet. Wow, that was super easy. This is the power of those special triangles. If you can create them, if you can find them in the diagram, in your everyday situation, you can very quickly get some very precise measurements for things there. Any questions on that example? Yeah. All right, then example 2. 2 planes take off at the same time. I should have specified from the same airport. Okay, they're leaving the same place at the same time. One travels due south at 480 miles per hour. A little bit slow for a plane. The other travels west at 550 miles per hour. That's closer to average. I did look this up to make sure my numbers were reasonable. Okay. How far apart are they after 1 hour? Ooh, okay. We're looking for a distance. Okay? We are given a speed, or rather 2 speeds. Okay? So we've got to keep in mind that we need to convert speed to distance. Why don't we do that now? Okay. So we know that velocity is distance over time. So if we want to solve for the distance, we'll multiply both sides by t. Right? This implies that distance equals velocity times time. You'll have more practice with that in physics. So for the first plane, let's call that distance 1, will be speed 480 miles per hour. Why don't we write that out? That's miles in 1 hour, right? Miles per hour. And we multiply that by the time that passed, which is 1 hour. Okay? Times 1 hour. Notice now the units work out. Hours reduced, and I'm just left with number of miles, so it's 480 miles. Oh, that's pretty convenient. I bet you guys could work out what distance 2 must be now, right? Can I get distance 2 there in the chat? For the second plane? Follow this same unit conversion process. What do you get?
It would be 550, right?
Yeah, 550, right? And I'm going to be lazy. I'm not going to show the computation for that. It's exactly the same as this, right? We can see, oh, miles per 1 hour times 1 hour. The number doesn't change, right? Nice and simple there. Okay, so we know how far they went, but we also have to keep in mind the directions, right? Did they go in the same direction, different directions, opposite directions? The first one travels south, and the other one travels west. So let's sketch that up here. So we have from the starting airport, plane 1 goes 480 miles south, and plane 2 went west, 550, so a little bit longer. This ends with 2. All right, good old compass rose, north, south, east, west. And this is now my vector diagram of the distances. But we can also see, hey, look, they shot at perpendicular directions to each other. And I want to know the distance now between each plane. So let's connect those endpoints. Okay? Call it distance 3. That's what I'm looking for. And once I've drawn that in, I can clearly see, oh, it's a right triangle. And I know the lengths of the two legs. I just need to get the hypotenuse, which means we're going to use Pythagorean theorem. Right? So that distance 3 will be the square root of 550 squared plus 480 squared. That is ginormous numbers right there. Holy cow. You could plug that into the calculator just as is. One trick I would do is I would say, hey, are there any common factors to these? Can I make the numbers a little bit smaller, just easier to work with and read off of? And yes, you can. Notice that they both end in a 0 there. So I'm actually going to divide everything by 10. I'm going to scale my triangle down smaller. And this is perfectly acceptable as long as you remember to do it to all 3 sides. So if I divide this by 10 and this by 10, I have to divide that by 10. So D3 here is not actually the square root of 55 squared plus 48 squared. D3 divided by 10 is the square root of 55 squared plus 48 squared. Okay, so whatever we get over here, we have to then multiply it by 10 again to get scaled back up to our full size distance between the airplanes. Okay. So D3 is 10 times that square root. All right, whip out the old calculator. I'm just using the app on the computer because it's convenient here. 55 squared is 3,025. 48 squared is 2304. So we add that, 3025. 10 times the square root of 5329. Okay, what is the square root of 532? Well, that's unexpected. I got 73. Did you guys get 73? Which means times 10, distance 3 is going to be 730 miles between the planes. Turns out we got a perfect integer answer from that. Apparently, 55, 48, and 73 is a Pythagorean triple, right? Who knew? Very convenient. I knew. I set up the problem. I made it convenient for you on purpose, right? But there you go. So but why you would want to find the distance between the, I don't know. It's just fun, okay? Maybe they need to communicate with each other and there's something with the radar. I don't know, right? Any questions on that problem? All right, then make sure you have your notes on hand to help you out because it is time for our quizzes. Let's go to, please go to joinmyquiz.com, enter the game code 283460. Genesis is first one in. Once again, 283460. All right, out of 17 students, we got 11. Take another 30 seconds to join in here. Okay, as always, you can use your notes, you can use your calculators. Retake code will be posted at the end of classes today, about 2:30. But let's see how much you can do as of now. I just want to see where you're at. Just from the reading, what do you remember? What can you do? No question here is a long problem like you'll have on your problem set. They're all fairly quick, short, and simple. Okay, when you are done, go ahead and transition to working on said problem set. That said, the 14 of you connected can begin. All right, and we're off. Oh, we got a correct answer to start it off. Nicely done. Okay, as they quiz away, that'll do it for the YouTube stream.